Okay, in this video we begin our discussion of projectile motion. This is part one of two videos. In this first one we'll take a look at just horizontally launched projectiles, do quite a few examples, and just discuss projectile motion in general. So a projectile, any object moving in two dimensions under the influence only of Earth's gravitational field. Its path, as is indicated by these three different pictures here, is a parabola. And of course, if there's no air resistance acting, if there is air resistance, that path would certainly change slightly. We'll study that as time progresses. So a projectile, any object that's rising and falling, but also has a horizontal motion associated with it. Probably our most common example of two-dimensional motion that we'll study in physics is projectile motion. Now, the motion of a projectile can be understood by considering the horizontal and vertical motion separately. So there is nothing changing the horizontal motion of an object. It will persist in the state of motion just as it did before. But once it starts to fall, as this diagram shows here, the object will actually do two things at once. It will both move horizontally at a constant rate and at the same time fall. And so the actual motion of that ball can do two things at once, just like you can. And it follows both of those kinds of motion, and it traces out a nice little parabolic path as shown. So the horizontal motion, as we expect, is a constant kind of motion. Vertical motion is accelerated due to that gravitational influence acting on that ball. Now, we learned different ways to add vectors, and I'd like to draw a couple of vector arrows over here. So let's draw a red horizontal arrow that indicates the horizontal velocity at this particular point. And, let's use this arrow there. And so at this particular point in its path, it's moving horizontally at that rate. And it's also acquired some vertical motion. And let's go ahead and draw that here. Some vertical motion that is right there. So those two velocities combine to produce a actual motion that is along that tangent line. Let's just go ahead and refresh your memory on how we draw that. So we complete, in this case, would be the parallelogram. And we could draw then an arrow here from one side to the opposite. That would represent the actual velocity at that point in time. And we could do that at every one of these points, and sure enough, what we'd see is a nice little parabolic path. Something that we have studied as well is just graphical representations of different kinds of motion. So let's refresh our memory here. Horizontally, the ball is moving at a constant velocity, and so we can go ahead and represent that graphically. Let's use red again. Horizontal motion is constant. The velocity would be a straight line graph like this, and there, of course, is no acceleration. If we call downward positive, then we can go ahead and graph the vertical motion as well. Here we'd expect a parabola. So y varies with time, sort of like this, and the velocity would be, of course, a straight line with constant slope, and the acceleration we'd expect to be g. And so just some graphical representations and some pictures over here to help make sense of projectile motion. Again, we analyze projectile motion by considering the two kinds of motion separately. Now we're going to do a couple of examples here doing just horizontal motion. Then when we get into angled velocities, angle initial launches, we'll have to do another video to show you that. So a boy jumps off the top of a rock ledge, 15 meters tall, jumps horizontally as shown here by this picture. He leaves at 3 meters per second. How far from the base of the vertical ledge did he enter the water? So let's just go ahead and use some of the color coding that we had from before. He jumps off with an initial velocity of 3 meters per second. I do have to make a general statement here. We have recently changed our technology, and it's no longer really convenient for me to write on the board, and so I'm having to do this with a mouse, and please forgive the messy notation here. So that is his initial velocity, and that is v naught, but in this case here, we're going to call it v naught sub x. Now, no matter where I look on this diagram, I could look at his horizontal velocity, and it should always be the same. There's nothing changing his motion in that direction. Now, vertically, as we saw on the other one, he starts with no initial velocity, and then as time goes on, you can certainly see the vertical velocity is getting greater, right? So, get rid of that. And so as he enters the water, he has two different components. One that's horizontal, same as what he had, and the other that's vertical. How we answer any of these kinds of projectile motion problems right now is to separate out the two motions and link them together through the time variable. I'm going to say that one more time. we separate the two kinds of motion and link them together through time. So let's see, it takes him a certain amount of time to drop 15 meters. This motion here is independent of his horizontal motion. So it doesn't matter that he jumped 3 meters per second here. His motion vertically is unaffected by that. Those two motions are independent of each other. So if I want to find the time he's in the air, I'm going to go ahead and use one of our UAM equations, because the vertical motion is a constant acceleration due to gravity. And I'm going to go ahead and just use this one. And again, please forgive that this is very sloppy. I'm going to solve this for time. And I get 2 delta y over g, take the square root. And so take that square root of 2 times 15, divide that by 9.8. Please forgive that I'm dropping my units. It's already hard enough to be able to write this as it is. And so what do we get for that value? So I grab my calculator, 30 and divided by 9.8, and just take the square root, is about 1.75 seconds. Now, during that time that he is falling, he is also moving horizontally at the exact same rate as he always was. So if I want to figure out how far he lands from the base of that cliff, I just use another UAM equation dealing with just a horizontal motion. Now here we have no acceleration horizontally, so I'm going to use the exact same equation as I used before. You might recognize this as a version of our equation 3 over on the board. In this case, since there's no acceleration, I'm just going to go ahead and use the first portion of that equation, which describes how the displacement is related to the initial velocity. And so this would be v naught x. He is traveling that way at 3 meters per second, and he's in the air for this much time. That 1.75 seconds is exactly the same amount of time as he's moving horizontally. So let's just link them together through that time variable. So I simply multiply that by 3, and I get about 5 1/4, maybe 5.2, maybe 5.3 meters. Okay, so how far he has moved in the air as a projectile. Let's take a look at this one. Stuntman jumps off a 25-meter ledge of a cliff horizontally. Rocks extend outward from the base of the cliff 12 meters. With what speed must he jump horizontally to achieve a 13-meter distance? So he's going to jump off of here and travel as a projectile. There's some rocks down here, so we want to make sure that he clears that by traveling at least 13 meters. Now he can jump again at some speed that we need to calculate. This is now the thing that we're looking for, is what is his initial jump speed. Just like from before, we're going to calculate the time that he is in the air by separating out the two motions and linking them to that time variable. So just like we had from before, time would be 2 times the change in y over g. And that looks like I'm writing it much better than I did before. I said I spoke too early. 2 times, let's see, 25 meters divided by 9.8. And again, just do some quick calculations there. Don't forget to take the square root of about 2.26 seconds. So if you've ever jumped off a cliff or anything high like that, 2.26 seconds is, feels like an eternity when you're falling. So 2.26 seconds in the air. Well, during that time, he's also moving horizontally at some rate. He's got to clear 13 meters. So let's go ahead and now switch it over to red to indicate our motion is now along the horizontal direction. And let's use the same equation as we used before. Now I'm just going to write it solving for v naught x. V naught x, the speed that he has to have when he leaves that cliff, would be delta x over time. And it looks like my mouse is definitely, the computer's lagging a little bit, so I apologize for that. Let's see, he has to travel 13 meters, and he has 2.26 seconds of time to do so. And so he must leave with at least a speed of about 5.7, 5.8 meters per second. So he's going to have to really get moving off of that cliff if he wants to clear those rocks. Okay, so again, linking the two motions through the time variable. Let's do one more here. Stuntman's jumping off a horizontal balcony into an in-ground pool. Stuntman's going to able to jump horizontally. In this case, we know the jump speed 4.2 meters per second. The pool is located 7 meters from the base of the hotel. From what floor should he jump in order to make it safely into the pool? We're going to say that safely would be an 8-meter jump horizontally so that he at least clears the edge of that pool. Now, you might not be able to tell. I am somewhat of a Photoshop expert. I could not find a picture on the internet that had a pool really close to a hotel. So this is, believe it or not, Photoshop. That pool is not actually there, part of that. So I know it's very impressive. Let's go ahead and see if we can't solve this problem. So he's going to jump. Let me redraw this. He's going to jump from the edge of that, from the balcony, and we have a pool here. Let's go ahead and just make that look like it's water there. And he's going to have to try to jump to a distance of, it's about 8 meters. So from here to about there, 8 meters of jump distance. I'm going to leave up here, and we don't know